Looks good.
Today we're going to be discussing the work that Dr. Raslev's group and Dr. Kim's group are collaborating with each other, which includes me, Dr. Raslev, Dr. Hahn, and Dr. Kim. We're going over the photodegradation, optically active polymers, specifically using time-dependent excited state molecular dynamics, photocleavable nitrobenzyl group, which serves as a phototriggering of polymers. The overall objectives is the group continues to work towards investigating polymer degradation mechanisms, computational method. In this specific presentation, we're going to go over a case study that we're analyzing as of right now, which is the photodegradation of 2,5-4-dicarboxylic acid, PCA, a direct polymer that includes nitrobenzyl chromophore using time-dependent dynamics. In this analysis, includes what we what information we've gathered so far, mechanism of photodegradation, fragments of this degradation process, and absorption spectrum, which we were able to calculate. The main ideas of this presentation are actually more application. Let's just say the theory and principles have to be discussed at a later time. Overall, just the view of this presentation is we're going to go over the previous experimental work that's been conducted. We're going to try to get the outcomes of the experimental work relating to computational methods. And the computational background, as well as the analysis, computational output of the and the relation to experimental results that was previously done, and then the conclusion. This work is still being conducted. There's still gaps, but hopefully I can explain, or at least give us ideas of what we've accomplished so far and why we're doing it. And so just a bit of an experiment's background. Previous work has been conducted by members of the ESU, members of the CSMS, TV, Dr. Webster, and Dr. Sigurd is in the audience, him as well. In general, what they've done is they've shown a principle, a proof concept where they could incorporate a bio-based building block, which is this FDCA unit, in red, 2,5-fran dicarboxylic acid, and they were able to polymerize it with a photo trigger, in this case, a nitrobenzyl group. They were able to photodegrade it and also recover that FDCA unit, which is also able to be polymerized again. So in our work, we're just going through this first process, this photodegradation process, to see if we can get the same outcomes as they have, or at least relate it, or see what sort of mechanisms cause this degradation process. A little closer look, but once again, the unit or the molecule that we're going to be looking at in particular is this nitrobenzyl group connected to the FDCA unit. And during their photodegradation process, they were able to compose and recover the FDCA. To relate, I had mentioned earlier about absorption spectrum. In their supporting information, during their article, they had shown that originally, before UV radiation was conducted, there's almost this white substance, and the color had shifted throughout irradiation. I think we were able to simulate that as well in our computational methods. So I would like to, the sound, okay. Maybe there's sound issues, hold on. I have a question. Does this sound better for everybody, or is this not as good?
That's better. You were kind of fading in and out.
Okay. Yeah. I will continue this method. Okay. So this let's say slide I'm showing is supposed to be a simplistic principles or ideas of what's happening. So on the left here is just supposed to be the circle in the middle is supposed to be a representation of an atom, and it has different orbitals. E minus is the electrons. And during this TDESMD process, which is the time-dependent excited state molecular dynamics, we're going to be exciting an electron from one orbital to say one that's further out, and then we're going to be de-exciting it back to its original electron. So what happened with molecules, in this case, I was just showing a simplified example of 2D representation. Again, on the right here, I do want to compare some methods. So on the top here, which is it's a molecular dynamics method where they show their calculations through energy increasing, but not actually going into an excited state. It's staying in the ground state. In the case of excited state molecular dynamics, it goes from a ground state to an excited state and stays there. What we're doing is from a ground state to an excited state back down again. And this process of going up and down is repeated. This repetition, which induces like a cyclic population and depopulation in the paired orbital, this changes the orbital occupation, which will vary the force between different atoms. Once the force is being changed, the resulting molecules exhibit photofragmentation. This is the view of previous computational has been done. Throughout the process, you can see degradation. Now back down again is repeated continuously. Once again, the work is not complete yet, but this is more towards application of this process that was previously developed. And I do want to just give an overview of, in general, we're going to have like two conformations of this molecule. So one is going to be in water. We're going to be looking at the mechanism of degradation, fragments. We're going to be analyzing the fragments and analyzing the absorption. The same thing will happen again with the conformation 2, but it's in a vacuum, just to compare and see any differences that exist. In the end, we're going to be combining it and compare with experimental results. So the next few slides, you're going to see it may seem a bit jumpy between conformation 1 and conformation 2. It's because I have portions that are significant, or at least able to be presented, and the portions that aren't. So I'm only showing parts and pieces of each. Okay? So I wanted to show just a general view of density of states. The red portion here, if any of you can see, is electrons inside of a particular orbital. I have labeled the orbital 112, 111, 110. This is actually our original HOMO, but not of a ground state molecule. And then our LUMO, which is 113, which these are showing unoccupied states, okay? Or unoccupied orbital. In each, in our case in particular, because I'm exciting from one orbital to another, we will be taking this red portion and putting it toward the different. Now, I just want to show you a view of kind of the orbitals that are going to be changing. And as you can see on the left, we have orbitals shown where I believe it's the pi bonds of the carbons in the Fran group have high electron density, whereas on the LUMO in its ground state, it's actually a lot of the atoms in that molecule. It's the different pi bonds relating to the carbons shown. You'll see the p orbitals, the oxygens of the carboxyl group, and you can see quite a bit of difference between the two. But in our case, the goal is, once again, to specify which electron, let's just say from 112, and put it to 116. And how this relates to, let's say, quote unquote, degradation. There's a possible trend that could be found from this jumping, okay? So I wanted to show, and I know this is a bit cumbersome and maybe difficult to read, so hopefully I can explain it well, is the first number, let's just say 112, 116, we had taken an electron from orbital 112, put it towards orbital 16. We were able to see this degradation process. Now the graph that we're seeing is just an absorption of, let's just say, hopefully we can find a trend between the absorption and sort of degradation. In this particular case, highest peak turned out to be a scenario where a large amount of degradation did occur. So, for example, these red X's are indicating which bonds had broken throughout the simulation. And you can see when electrons had jumped from a differing orbitals, let's say 111 to 114, very few degradation, or excuse me, very few bonds have broken through that. So in our original kind of view of this process, in this case, the vacuum simulation that we've conducted, I focused on 112, 116, because it seemed to be the most degradation. The part of this work that we're trying to do is kind of see if there's any physical or quantum or molecular example or trend that we can find that can relate to this mechanism degradation process. I did need to show, let's just say, the orbitals as an example of possible trend finding, where in this case of the conformation 1, which is the water, we were able to, in this case it's the conformation 1 water, and you can see the different orbitals. I'm going to explain that on the far left, where it's red, is these are two views of the same molecule. This is two views of the same molecule, and it's the same for the portion on the right. I just wanted to hopefully give you a different view of the same molecule and the orbitals involved, and see how there is a difference between these different orbitals. In this conformation 1, you can see how the p orbitals are shown in the Fran group, and this somewhat shown in the Fran group as well on the orbital 167 compared to the 162, but the pi orbitals in 167 is shown compared to 162 of the Fran. Just see some differences. Maybe there's some trend or thing that we can find throughout this. Similar concept, I wanted to show the conformation 2, which is in vacuum. You can see how between the orbital of 112 and the orbital of 116, we would see the electron density being large between previously mentioned the carbons of the Fran group, and then orbital 116, you can see though that electron density is around the Fran group, different positions such as the pi orbitals of the carbon and carboxyl group, and the p orbitals of the carbon-carbon bonds of the Fran group, and oxygens, and so on and forth. Once again, my analysis still needs to go further and see what trends we can find or what information we can get. I want to explain just on this slide the basic simulation, or it should be the fragments that were produced of our simulation. In this case, we had focused on the orbital jumping from 162 to 167 with the conformation 1, which was in water. And you can see we got two fragments that were shown at one point in our simulation. The bond that had broken, which is the oxygen of the carboxyl group in the middle, and the benzyl group in benzyl carbon in the nitrobenzyl group, we were able to disconnect that and produce the FDCA unit we had previously mentioned, which is similar to, which matched what was being done in the experimental work previously mentioned. These blue arrows are just to kind of give you a flow of what was the mechanism or what had happened, where this original carbon had been, let's just say, the bond between the oxygen, carboxyl oxygen, and the benzylic carbon had broken, and so it had an open vacancy where the oxygen of the excited water was able to interact with this, and they were able to bond and form this unit below. An oxygen in the nitro group had decomposed and actually gone back and interacted with the hydrogens that were available in our simulation. So it was left with the nitrosyl group, which is part of the benzene unit you see below. Now this was for the interaction within water. I want to go into what happened with the vacuum portion. This is just when it's just the molecule, right? So this, I was analyzing it, and I believe this is a portion of just overcooking in the concept. Multiple fragmentations did occur. The fragments don't seem to match what experimentalists have found. But as you can see, numerous fragmentations with CO2 And I'm about to explain the difference between the last slide I showed you and this one. So the previous slide had shown that a fragmentation did occur, correct? Well, in this case, four bonds had broken not early, at one point in our simulation. So rather than one bond being broken, like in the previous thing or slide I had mentioned, this one had four happen at almost simultaneously. So there's a different mechanism that's happening. I'm still analyzing and trying to understand why and what had happened. And the further fragments that you see are just further along the simulation. But comparing the first fragmentation slide I had shown you and this one, you can tell there is a difference between the two already. I had mentioned we wanted to look at the absorption spectrum. In our case, quantitative, let's say, calculations are possible, but we decided to go with the qualitative version, which is, as you can see here, the absorption before excitation, which mimics this or not mimics, is let's say, more in the blue area. And then as we do our calculation and after excitation, we do see a shift to what would mimic this red shift that we saw previously in the experimental work that was done. An added, let's say, uniqueness to this TDESMD method was to look at MassSper, or time-of-flight mass spectroscopy. Now, this was the water version of this, and if you guys can see on the bottom is the molecular weight, not the top is the amount of time it was a part of the simulation. So, for example, at 0, you'll see this high peak, which I believe is hydrogen. So you'd see a high peak because they were part of our simulation for a very long time. And to the right here, you'd see the water molecule. It's very high peak as well. And throughout our simulation, you'd see different molecules form and decompose or come back together. I wanted to emphasize the location of FDCA molecule. Though the peak does not seem to show here, we did see it in our simulation. So I do need to analyze this a bit more, understand what is happening because it was shown. More work can be done, but I do want to express that we have this opportunity that has been previously done and researched where you can simulate this time-of-flight mass spec. I personally just have to do more analysis and see what's going on. Whereas in the vacuum or TDESMD 112, 116 mass spectroscopy, we see that all those different fragments were shown throughout our simulation, or most of them. For example, the CO2, the NO2, the NO2H had obviously a very large peak throughout our simulation. So this work, the conclusion and the future work that needs to be done is computational trajectories have been conducted. Okay. Photo cleavage of the molecule was seen in vacuum and water simulation. Redshift was seen in the absorption spectrum of the water simulation conformation. Further analysis of the photo cleavage mechanism will be conducted in both water and vacuum environments. And then further analysis of the fragmentation will be conducted. This would include the mass spectroscopy as well. And I need to acknowledge all the people that have been working well with me and all the funding sources, such as my advisor, Dr. Rosala, Dr. Cuum, Han, a couple partners of mine, the departments supporting polymeric materials, Center for Sustainable Materials Science, North Dakota State University, Andy Epscores Awards, National Energy Research Scientific Computing Center, which is known as NERSC, and then the other funding source of NSF-CHE 1944921. Okay, so that concludes what I have. Any questions?
All right, thanks, Meade. Does anyone have any questions?
I will just make a comment. FDCA doesn't really, in typical ESI, it doesn't show up. It doesn't ionize right. So when you see nothing for FDCA, it's because it's not ionizing properly.
Okay.
And then in terms of some of your fragmentations, I mean, so for example, in this slide, I mean, what is the probability though? I mean, don't you compute some kind of a potential for these kind of fragmentations?
Well, it's a good question. Whether it be probability, I'm not for certain. The main idea is we simulate it and we see what we get, and then we analyze it after. And whether it be maybe there's something we could do beforehand with probability, I'm uncertain at this point. I don't know.
It's similar to what my colleague John Hirschberger does. You know, he does a reaction with some reactive molecules, and then he has like 15 different pathways, and then he computes essentially what's the probability of that reaction occurring. It could be 1 in a million, whereas the other ones will have 1 in 100. So yes, these are potential, but if the probability is close to 0, then it makes it's of no use.
Oh, okay. Well, that's a great tool that I could look at. Thank you.
Yeah.
All right, any other questions?
May I contribute to discussion on the last question?
Sure.
Okay. So the procedure that Meade is doing is able for immediate providing of the time of the specific reaction step, and if the time from the beginning of simulation to the instant of the specific bond breaking is long, it can be interpreted as a low probability. If it happens immediately after short time, it can be interpreted as high probability. And this is the quickest information available from simulations that Meade is doing, which can be later on summarized in like branching pathways and probabilities for different channels. So time when it is a time-dependent simulation and reaction happens at a specific time after simulation starts. So this time is indirect metric of the probability. Okay, I'm done with the comment.
Well, thank you.
So, to go back and then comment on your comment, Dimitri. So to make a comment on your comment. So suppose your reaction takes place, you know, like, okay, in the first 10 nanoseconds, 95% of the fragmentation has occurred in a different pathway. And then in a couple of nanoseconds later, something else comes in. Then really have nothing there, right, at the end. The probability of that going through the second pathway is very small.
Yes, there should be additional steps to decipher individual reactions from this trajectory, but one can measure time intervals between different steps and start from there.
Yeah, interesting. You know, we had similar questions when you were presenting the other day.
Mm-hmm.
Yeah. No.
All right, any other questions or comments? You have another question, Mook?
No, I'm trying to lower my hand.
I already lowered your hand for you.
Thank you.
Thank you.
All right. So thanks, Meade. Appreciate the presentations today. And we will look forward to our next meeting. Just to give you a heads up, November 18th, since November 11th was Veterans Day holiday, we had to shift the meeting to the 18th, which I think creates some conflicts for some people. But on the schedule are the Oven group, the parent group, and the Kubatova group. So just keep that in mind for next month. And unless anyone has any other comments or announcements, we will say goodbye.